Okay, so finding the nearest neighbor. So the algorithmic efficiency issue. What I'm going to show you essentially falls into the class of techniques called branch and bound. Okay, so branch and bound. Okay. Now, the idea is that there's a pre-processing step which puts the data into a nice, convenient geometric form. Okay, so let's start by imagining that the data has been put into this nice geometric convenient form, and that presupposes that it can be put. So it's possible to put the data into this form. Okay, and we'll address that issue next of how do we put the data into this form. Okay, so imagine that the data points look like this after I've put them into this form, and you'll get the picture of what's going on very quickly. Okay, so there's the data points. Some data points are like this. Okay, and then some data points are like that. Okay. And so when you look at this, you're going to be thinking to yourself, that looks like clustering. Yes, and that's going to play a role here. Okay, so, imagine that we have two sets of data. Let's imagine them to be called clusters for whatever reason. Okay, so let's call this cluster S1, set 1. Okay, so this is set 1. Okay, and this is set 2. Okay, and, associated to every cluster, you have a central point. So let me, put the central point. And we will call this mu1, mu2. Okay, and you can think there's also a radius. So there's a radius, R1, R2. Okay, so, you might say, well, how do we know the data can be put into that form, and how are we going to get it into that form? Well, those are issues we will address later. For the moment, I just want to describe for you the branch and bound technique. Okay, so, this is the data, and the goal is to find the nearest neighbor quickly. Okay, so let's suppose that we have a test point x, okay, and x is going to be closer to one or other of these clusters, of these groups of data points. So let's imagine that x is closer to S1. Okay, so now we're looking for the nearest neighbor to x. So the natural thing to do is to start by looking for the nearest neighbor to x in S1. So you jump into S1. So jump into S1 and find the nearest neighbor to x, and find its nearest neighbor to x. Okay, that's a set of points. Okay, we can certainly, solve the nearest neighbor problem just restricted to S1. So let's say that returns x1, and remember we called it x1 in square brackets, so x square 1. Okay, but now we don't know if that's the true nearest neighbor because it's just the nearest neighbor in S1. There could be a closer point in S2. So let's call that our temporary nearest neighbor, x square 1 hat. Okay, it's our conjecture for the nearest neighbor. Okay, now this jumping into S1 and finding the nearest neighbor in S1. Okay, that's the branch step. So this is called the branch step. That's the branch step. If you can think about it, I have two branches and I'm going down one of the branches. And so that immediately generalizes if the data is, represented not just as two sets, but as a number of sets. Let's say K sets, K clusters. Okay, but I'm just illustrating for two. You'll get the idea. Okay, so now what do we do? Well, the simplest thing to do is now that we've got an x1 hat, go into S2, go into the second set and find the closest. Okay, but then that's, how have we gained? We're going to be comparing, x to every data point. Okay, and so this is where the bound step comes in. So the bound step. Okay, and, the question we ask is there a criterion that we can quickly check, okay, that will tell us whether or not we need to go into the set S2? So is there a quick criterion to bound the closest point so we can check quickly if we need to go into S2. Okay, so that's the goal, that's the idea. Okay. Now, let's think, what's the closest that a point in S2 can be to x. Well, there's the distance to mu. Okay, so the closest, and that's where we get this notion of the bound. The closest point in S2 has distance, has distance, x minus mu is the distance to the center, but then it can come back at most a distance r2. Okay, so you can, the closest point is the point that is, if you take x and send a ray to this radius and then come back, to this point where you hit at the surface, that's the closest point. Okay, so the closest point in S2 has distance x minus mu2, okay, minus r2. That's the closest point in S2 to x. I mean, not necessarily the closest point, but that's the closest any point can be if it's in this set which has a radius of r2. Okay, as an upper bound of r2. Okay, so let's think about this. If this bound, if the closest point or the closest distance that any point can be is greater than the distance we found, if this is greater than or equal to even the distance from x to, the closest neighbor, x1 hat, x square hat, if this is greater, then we're done. We don't even need to go in there. So this is called the bound condition. This is called the bound condition. Okay. And so look what we have done. We went into S1, we got the closest neighbor x hat square 1, okay, and then we check the bound condition. Okay, if the distance that we have already achieved is less than or equal to the minimum distance to any point in this set, which is given by this bound, which is lower bounded by this bound. So if you've already accomplished this, there's no point going in there. And so we save ourselves a huge amount of search. Maybe half the search could be saved. Okay, so if this bound condition holds, if this holds, implies you don't need to search S2. Okay, and so we have saved roughly half the work. Okay, and that's it. That's the branch and bound algorithm. Okay, now let me just mention that this is a very ongoing, cutting edge research issue, which is how to find the closest data point to a given test point quickly, how to store the data efficiently. So we'll study that shortly. And this is a mechanism that is sort of in some sense guaranteed to work. Okay, the failure probability is 0. The only problem is that if the bound condition does not hold, then you may have to search S2 and you haven't gained anything. Okay, so that's the first thing. So first observations. It is guaranteed to produce the nearest neighbor. So produces nearest neighbor. And that's a guarantee. Okay. The second thing we can observe is that, there's nothing to stop this process from occurring recursively. So when we jump into S1, S1 could also be stored as, a pair of, or maybe 3 or 4, maybe 3 or 4 clusters, subclusters. So we can hierarchically run the branch and bound algorithm. And that's usually how it's done. And that's how you gain the most savings. Okay, because it's not that, so you'll gain a factor of 2 here, and then you'll gain a factor of 2 here, and a factor of 2 there, and a factor of 2 each time you go down. And so it results in a potentially logarithmic search time instead of linear search time. So you can do this recursively. Okay. Now, what's the sort of bad news? The bad news is, it's guaranteed to produce a nearest neighbor, but the worst case runtime can be order of n. So you may not have gained anything. Worst case runtime can be omega of n. So you may not gain because you may come out of here, and each time you come out and check the bound condition, it fails. So each time you come out, you have to search the other set, so you don't gain anything. Okay. Now, part of that is because we want an exact algorithm. The algorithm must work. Okay. So some of the areas in which research is done are to say, well, can we relax some of these conditions and get better algorithms? So how do we relax? Maybe we can say, you know what? with high probability, your algorithm's running time is logarithmic. Now, this particular algorithm, if you have good clusters, it turns out that the expected running time is logarithmic. But maybe we can get with high probability logarithmic, or even with high probability constant running time, okay, depending on assumptions about the distribution. Okay, so that's one way in which you can try to improve the algorithms. In other words, the algorithm almost always finishes quickly. Okay, and that's this kind of algorithm. Almost always finishes quickly with the exact answer. The other way in which you can relax these conditions is to say, you know what, I want an algorithm that, always finishes quickly, but what you must guarantee is that it doesn't necessarily produce the nearest neighbor, but if it produces a neighbor, there is no other data point that's, let's say, a factor of 2 closer. Okay? So it produces an approximate nearest neighbor in that sense. Okay? So there's a lot of research in how to relax the requirements of the nearest neighbor algorithm to make it more efficient. But then when you relax those requirements, what happens to the E out, being nearly optimal? So then that's another issue is, to analyze how the algorithm, if you relax it and don't produce exactly the nearest neighbor, well, then will you still be able to get the near optimal convergence? Okay. So that's, the sort of, basically, in some sense, what's going on with respect to the research in this hard problem. Okay, but now let's get back to our algorithm, which is a relatively simple algorithm, and ask 2 questions. When do we gain? Okay, and by studying when we gain, in other words, when does the branch condition hold, that'll tell us the condition that we need for these, sets, the geometric condition that we need for these sets. Okay, and when we have that geometric condition that we need for these sets, then we can say, how do we set about putting our data into that format? Okay, so when do we gain? We gain when the branch condition holds. Okay, so let's see, when does the branch condition hold? When this is true. Okay, so we gain when this is true, when, x minus x hat 1, let's see, x minus x hat 1, x minus x hat 1 is less equal to, x minus mu 2 minus r2. Okay, that's when we gain. Okay, and I'm going to observe that x minus x hat 1 is at least as large. Okay, x minus x hat 1 is less equal to, x minus x hat 1 is less equal to the distance from x to the center plus r1. So this distance. Okay, so this is less equal to x minus mu 1 plus r1. Okay, so this guy is less than equal to that. And if this guy is less equal to that, then for sure this guy is less equal to that. So the bound condition will hold. A sufficient condition is this condition. So I've simplified because I want to analyze, when does the bound condition hold. Okay, so it suffices that x minus mu 1 plus r1 is less equal to x minus mu 2 minus r2. So let's rearrange. r1 plus r2, r1 plus r2, okay, is less equal to, and we would typically like it to be much less than, okay, so r1 plus r2 is less equal to x minus mu 2 plus, minus x minus mu 1. Okay, so now let's look at what's going on here. Okay, so this is x minus mu 2. Okay, so this is x minus mu 2. X minus mu 2. Okay, this distance here is mu 2 minus mu 1. Okay. And now the reason, now this is just heuristic because I'm just trying to understand when will the bound condition hold. Okay, so this guy minus this guy, so this guy minus this guy. Okay, so if this guy is small, and that's why we went into S1, so this here is x minus mu 1. So if this guy is small, okay, then this distance is approximately that distance. Okay? So this guy here, now this is just heuristic. I'm not claiming any rigorous argument here. I'm just trying to understand when do we expect the bound condition to hold. This guy here is approximately equal to mu1 minus mu2. Okay. If you want to think about it in a sort of slightly more interesting way, you can say that we know that a minus b in magnitude is at least the magnitude of a minus the magnitude of b. Okay, so here we have magnitude minus magnitude. Okay, so if this at least is almost saturated, then you get, let's say, an approximately equal to. So this minus this is approximately equal to this, the norm of this minus that, and the x's cancel, you get mu1 minus mu2. That's sort of geometrically, suggested in this figure. But none of this is rigorous, by the way. This is just to try to understand what's going on. Okay, and so, approximately the bound condition that we want, so when will the bound condition typically hold, is when R1 plus R2 is less than or equal to, or much, much less than, mu1 minus mu2. Okay, so I'll just box this. Okay, this is when the bound condition is expected to hold often, okay, quote unquote often. Okay, and now let's analyze that. So what's R1 plus R2? R1 is sort of the size of cluster 1. R2 is the size of cluster 2. So in some sense, R1 plus R2 measures what we call the within cluster spread. So typically we call this the within cluster spread. Okay. And what is mu1 minus mu2 in magnitude? It's the difference between these two centers. So that's how far apart, okay, the clusters are. So this is sometimes called the between cluster spread. Sometimes we call this the intra-cluster spread, INTRA cluster spread. And sometimes this is called the inter-cluster spread, INTER cluster spread. Intra meaning inside, inter meaning, between, okay, from one to the other. Okay, and this is a very intuitive condition. Okay, what is it saying? That a branch and bound algorithm is likely to give us the biggest benefits, and especially if you incorporate it in recursively, okay, when your data can be stored in sort of sets of this form, such that the sets themselves are very tight. So their internal radii are small, so they're tight clusters that are well separated. Okay? So the distance between the clusters is large. Okay? And so this tells us that from the perspective of getting big savings in the branch and bound algorithm, you should try to structure your data and store it in these clusters that are tight and well separated. Okay, so now in seeking to sort of get data into the right form, we can try to optimize that criterion, try to find clusters that are far apart, okay, and tight. Okay, and that is called a clustering criterion. And in fact, even though we derived that clustering criterion from the perspective of making a branch and bound algorithm more efficient, that is actually one of the most commonly used criteria in order to find clusters in the data. Okay. So now, let me show you an algorithm that basically finds clusters in a data that is trying to get this branch and bound criterion to hold as much as possible. Okay. And this algorithm is called Lloyd's algorithm. Okay. So let me erase. Okay. I'll just put the criterion here. Okay. Summary. So the summary of this criterion is that we want R1 plus R2 to be much, much less than mu1 minus mu2. Okay, and then I can erase here and show you an algorithm that attempts to do exactly this. And we are motivated into this algorithm because we want to make branch and bound more efficient, but actually this is a very general criterion that we use when we try to cluster, when we try to organize the data. So good clusters are tight and well separated.